Let's have a look at another tool which is called derivative overlay. So let's say I've got 3 PBUs here, and on this log plot or derivative plot I plot the data from this PBU. So I've got delta P plot, which is this pressure signal here, pressure at T minus pressure at J, and its derivative with respect to a time function. And I plot this versus the shut-in duration delta T. Okay, so now I can overlay on the same plot the data from these two other PBUs. And so with the code color, you're going to see the data from the first PBU in pink, which is this one, the derivative and the delta P plot, as well data from this PBU in dark blue. This is quite a powerful tool. It gives you some confidence in the data. By plotting all the data from the different PBUs, it's going to be easier to spot your stabilization in the derivative, so to spot random flow regime, and to spot any dynamic changes between this PBU. So for example, remember the vertical separation between this stabilization and the delta P plot is indicative of the skin. So here on pink, if you look at the pink and the green, you might say that this vertical separation is increasing. So maybe our skin is increasing between the two. As well, you could see that the hump as well is increasing, so that's indicative of more damage. And also you might argue that the derivative plot here is getting higher, which means that your cage is getting decreased near well bore at shorter delta T. And that could mean that you've got maybe gas breakout in the reservoir, reducing your effective permeability to oil. So simply by looking at the plot without doing any further analysis, by looking at the derivative overlay, you can monitor well performance. You can also assess the impact of well intervention. We've seen this with our example of limited perforation. And you can also QC your rate measurements before each PBU. This plot is rate normalized. So we divide the pressure and its derivative with the final flow period before the PBU. Okay. So all the plots should share the same stabilization, indicative of radial flow regime. Okay, so this is dictated by kH and the fluid viscosity. This is dictated by the reservoir properties. If they don't share the same stabilization, well, that could mean that this is not radial flow regime in the horizontal plane, or that you've got a change in well performance, like for example reducing your effective permeability to oil, or that your rate is not correct. When your rate is not correct, what you'll tend to see is a parallel shift in your response. Okay, deconvolution. So here I've got my derivative overlay, and I can derive deconvolution for each PBU. But let's assume I'm deriving deconvolution for this final PBU. And this is the red response here on the plot. So if you like, deconvolution is a sort of improved derivative. You see some discrepancy between the deconvolved derivative and the conventional derivative. And this is because in the conventional derivative, you might see some errors, or what we call distortions. And this is because of the way this conventional derivative is calculated. On the deconvolution, without entering too much into details, deconvolution will give you a sort of pure signal. It's going to be free of any error. So it's going to help you to improve the PTA understanding. It's free from any errors. But as well, if you look at this deconvolution response, it's derived over a longer time interval. And actually, when I derive deconvolution from this PBU, duration of this deconvolved response is going to be equal to the duration of the entire test sequence. Okay, so in this case, we've got 300 hours. And now you see a deconvolved response, which is developed over. Here we've got 100, 200, 300 hours on the log scale. Okay, so now you see further away from the well, and you can add reservoir insights. As well, without entering too much into details, deconvolution will help you to refine the initial pressure. As for any other tool, deconvolution has some limitations. Okay, so you need a bit of expertise to recover reliable deconvolution.